Alright, let's take a look at a problem where we have some mass m and we're going to drop it some distance. So we'll call it some initial distance h above the ground, but we might not be dropping it all the way to the ground. We want to know what is the speed at any point above the ground or at the ground. So let's take a look at, let's draw maybe its position in some other space. We can call this 1 and this 2. And let's call this distance y. Alright, if we call this y is equal to 0 down here, I kind of really recommend setting the ground to 0, or at least one of the positions, 1 or 2. I'm driving a formula for any position, so I'm just going to use h and y for now. And it'll be this distance y with respect to h always, right? And that's what I'm going to show you. If we say it is initially at rest, we want to know what's the speed at any point. Well, let's do what I taught you. Kinetic energy initial plus whatever potential energy initials we could have. Kinetic energy final and potential energy final. Alright, it's at rest, so boom, we get to cross out the kinetic energy. For the potential energy, look at the problem. Do we have a spring? No. Do we have gravitational potential? We do. So let's go ahead and put some mg h term. That's some h in its initial state. And that's going to equal some kinetic energy at some any other point 2 in space. It could be anywhere, right? And it doesn't have to go all the way to the ground. It could go to some distance y. So measured from the ground, what we called y is equal to 0. Every term has mass. Make sure they all have mass before you just cancel it out. If there's a spring in the problem, that means you can't just cancel the mass out. There's no mass in the spring energy term. Okay, and we can then rearrange this. V final is equal to the square root of 2g, and then this is h minus y. And what we'll find out is for whatever y you pick, we could have called y down here is equal to 0 and measured from here, or we could have called y is equal to 0 up here. In this case, we would have had negative potential energy terms, which I try not to do. I try to always keep my gravitational potential energy terms positive, or at least greater than or equal to 0. How about that? I try to make one of them 0 if possible. That's basically a trick. If you can call one of them y is equal to 0, then it now has no potential energy in that state, and we don't have to worry about it. We get to cross it out. But we find out that in general, the final velocity of something that's dropped some distance, delta y, is just the square root of 2g times that change in position. Okay. Looking at the next part of the problem. Part B says, what if it had some initial velocity? The initial velocity is an upward speed also. So what if we threw this mass up? Well, we don't care about the sign of the speed at all. All we care about is the energy. So we would say the kinetic energy plus potential energy is going to equal the kinetic energy plus potential energy. And what do we have? We have a 1/2 mv squared term, and this is our initial. We still threw it from some mgh maybe. So that part of the problem didn't change. It still started up high, got thrown, and then we figured out the speed at any other point. And that all equals some 1/2 mv final squared plus the potential at whatever y it is. And once again, mass is not a factor in this, or is a factor basically. It is independent of mass, and we can cancel it. We get a final velocity equal to the square root of the initial velocity squared plus 2g, and then that would be our delta y again, or delta y is equal to our h minus y. All we had to do is throw this extra term in. Initially it was from rest, so we crossed it out. For any initial velocity, we just throw it in there. But if this is something like a projectile problem, we need to look at the directions. So we would want the velocity in the y direction if we wanted to know how high it went or something like that. So you do have to break up the 1/2 mv squared into the components every once in a while, and the projectiles, one case, that's about it. Basically, if they wanted to know how high a projectile went and launched with some initial velocity at some angle theta, take some parabolic path, and they want to know what h is. Well, we can't put in v. We can't say that 1/2 mv squared is going to turn into mgh. We can't say that. We have to say 1/2 mass times velocity in the y direction squared will give us that maximum height, and then we can solve for that maximum height. H is equal to v squared over 2g, but that's got to be the y direction.